So the last part of section 5.4, we're going to be taking integrals of exponential functions. I think you'll find these to be pretty much just as easy as taking the derivative of exponential functions. So let's take a look at theorem 512, okay, integration rules for exponentials. Once again, two different versions. The first one is the most basic, when it's just e to the x, so we're going to integrate e to the x dx, and you're going to get e to the x plus c. The second one is for if we have anything else in that exponent. So the integral of e to the u du is going to equal the integral of e to the u plus c. We'll kind of see how that plays out as we do some of the examples here. Okay, first example, notice that it is an indefinite integral, so there's no limits, so we got to make sure that we always include the plus c there. So for us, okay, we're going to use u substitution, so we have the integral of e to the 3x plus 1 dx. So we're going to let u equal 3x plus 1, take the derivative of u with respect to x, so du equals 3dx, and then we have to be able to replace dx, so we're going to replace dx with du divided by 3. So now we're going to rewrite that integral, so that integral comes out to e to the u times du over 3. Just like we've been doing with all the other integrals, pull the 1/3 out in front of the integral, so it's going to be 1/3 the integral of e to the u du. That equals 1/3 e to the u plus c. That's the antiderivative. And then we have to plug in what u was back in. U was 3x plus 1. So our final solution is 1/3 e to the 3x plus 1 plus c. Let's move on to example 18. We have the integral of 5x e to the negative x squared dx. So always choose u to be the exponent when you're doing an exponential here. So u is going to be negative x squared, so du is negative 2x dx. And then we have to replace x dx. We can't replace that 5, it's fine, it's going to sit there. But we can replace the x dx with a negative du over 2. So we're going to rewrite the integral in terms of u. So we're going to have the integral of 5 e to the u times negative du divided by 2. We're able to factor out that 5 and that negative 2, or negative 1/2, excuse me. So you're going to have negative 5/2 the integral of e to the u du. Very simple for us now. The antiderivative is going to be negative 5/2 e to the u plus c. And then we substitute our u value of negative x squared back in. So our final solution is going to be negative 5/2 e to the negative x squared plus c. Looking at example 19. And once again, these should all follow similar homework problems in your book. We're going to have the integral of e to the 1 over x divided by x squared dx. Still choosing u to be the exponent on e, so u is going to be 1 over x. When we take the derivative of 1 over x, we get 1 over x squared dx. So du is going to be 1 over x squared dx. That's a perfect substitution. So this one works out really nice. We just rewrite the integral as e to the u du. Then we take the antiderivative of e to the u, which is e to the u plus c. So we end up with e to the 1 over x plus c because we're substituting 1 over x back in for u. So looks complicated, very simple piece on this one. Example 20, we have the integral of e to the 5x times 5 dx. U, once again, exponent of e, so u is going to be 5x. Du is going to be 5 dx, perfect replacement there. So we can just rewrite the integral as the integral of e to the u du. And the integral of e to the u is e to the u plus c. And we substitute 5x back in for u, so we end up with e to the 5x plus c. Hopefully you guys don't find these too challenging. Next, example 21, we're going to integrate x squared e to the x cubed dx. So when we do that, once again, u is the exponent on e, so we're going to choose u to be x cubed. Then du has to be 3x squared dx. Notice we're only going to replace x squared dx in the integral, so we have to make sure that we use du over 3 is equal to x squared dx. So when we do that substitution, Make sure we're just paying attention to the little things like that. So rewrite the integral. So we have the integral of e to the u times du over 3. We can factor out that 1/3 and have 1/3 the integral of e to the u du. Then we take the antiderivative, so it'll be 1/3 e to the u plus c, and we replace u with x cubed, so we will have 1/3 e to the x cubed plus c. Let's look at example 22. A little different on this one. Now we got some limits of integration. Okay, so we're going to take the limit from 0 to 1, or not the limit, I'm sorry. Well, we have limits of integration, yes. We're going to take the integral from 0 to 1 of e to the minus 2x dx. Same procedures. We're going to let u equal the exponent, so u is going to equal negative 2x. du is going to equal negative 2 dx. We have to replace dx exactly, so we have to use du over negative 2. Now we're not done. We have limits of integration, so that means we have to write those limits in terms of u. So we're going to take what we selected for u and plug our lower limit in, which is 0, and plug our upper limit in, which is 1, and get our new values of integration. So when we do that, we plug in 0 in for x, you get negative 2 times 0 is 0. We plug 1 in for x, we get negative 2 times 1, which is negative 2. We're going to rewrite this integral a couple times. I'll explain why here in a second. Our initial integral, we've replaced the upper and lower limit. Make sure that you replace them exactly. 0 has to be the lower limit, and negative 2 has to be the upper limit. So when we write this integral, it's 0 to negative 2 of e to the u times du over negative 2. Okay? We're going to factor out that negative 1/2. So we're going to have negative 1/2, the integral from 0 to negative 2 of e to the u du. Now, the next piece is a property of integrals. When we first learned integration, I can switch the limits and do the opposite in front. So, since that's a negative 1/2 in front, I can do the opposite and multiply it by a negative and flip the limits of integration. So, it now becomes 1/2 from negative 2 to 0 of e to the u du. And now we just do our antiderivative and evaluate it. So we're going to have 1/2 times e to the 0 minus e to the minus 2. If you substitute all that into your calculator, you get 0.432. So this problem, it's really kind of in the middle. You have to remember that property for integrals so that we can switch the limits of integration back and forth as long as we do the opposite. And also, since we have limits and we use u substitution, we have to make sure we find our new limits in terms of u, not in terms of x. Alright, last couple of examples here, and then we'll wrap it up with integrating exponential functions, and we'll be done with chapter 5 for now. So, example 23, we have the integral from natural log of 1 to natural log of 3 of e to the x dx. So, there's nothing really complicated about this integration. We take the antiderivative of e to the x, it is e to the x, and we evaluate that from natural log of 1 to natural log of 3. So when we substitute in, that's, f of b minus f of a. So we have e to the natural log of 3 minus e to the natural log of 1. Now remember, e and natural log are inverses, so we can rewrite that. The e and natural log cancel each other in both scenarios, so we end up just writing 3 minus 1 equals 2. You can actually put that one into your calculator and check as well. I haven't been telling you that, seeing who's watching the videos. All your calculator will do all the integrals when there's limits of integration. So you just have to hit the math button, go down to, I think it's number 9, which is finite integral, select that, input your values, and Yahtzee, the calculator will do it for you. That will really help on the next problem. Example 24. Okay, this one's very, very similar to a problem that you have on your homework. It's probably like the last 2 problems on your homework assignment for this. Alright, we have a valve on a storage tank is open for 4 hours to release a chemical in a manufacturing process. The flow rate R in liters per hour is given by the linear model natural log of R equals negative 0.6155t plus 6.0609. We want to write the linear model in exponential form, so that's the first part. Then we want to use the definite integral to approximate the number of liters of chemical released during the 4 hours. So there's two parts to this problem. We need to take that linear model, write it as an exponential model, and then we need to integrate that exponential model. Okay, so this one stems back when we do the solution about being able to rewrite natural logs as exponents and back and forth. So our best bet in this case, since we want to write it in exponential form, that's kind of the key word here, okay, we want to exponentiate both sides using e because we have natural log. Okay, so we're going to raise both sides to e, or have e be the base, for both sides. So we're going to have e to the natural log of r equals e to the negative 0.6155t plus 6.0609. Now remember, on the left hand side we invoke the inverse property, so e to the natural log cancels and we're left with r, and r is equal e to the negative 0.6155t plus 6.0609. Now what we have to remember here is we're undoing the exponents. Okay, so when we undo the exponents here, you'll have to go back and take a look here. We're taking a look at theorem 510. I've kind of moved the screen on you here a little bit. This is the property, the first one here, so theorem 510. We have e to the a times e to the b equals e to the a plus b. Well, our situation has an e to the a plus b. Okay, so we're going to use that. This is on page 3 of your notes. So if you go back and look at page 3, this is where it's coming from. We're going to take our e to the ab and write it as e to the a times e to the b. So now we looked back at that piece. We have e to the minus 0.6155t plus 6.0609. That's our a and our b. Now we're going to rewrite that as multiplication. So e to the a times e to the b. Okay, so that's how we go from one step to the next here, taking a look at those properties 510 on page 3 of the notes. Alright, so when we do that, r is equal e to the negative 0.6155t times e to the 6.0609. What happens? We evaluate, since the e to the 6.0609 is a constant, we can actually use our calculator to get that value. When you do, you get 428.76, and so that's why r is 428.76 e to the negative 0.6155t. So that's part 1. We took the linear model and rewrote it as an exponential model. Now we want to do the integral for 4 hours. So we're going to integrate from 0 to 4 of r of t dt, and we just calculated r of t, so we're going to integrate from 0 to 4 of 428.76 e to the minus 0.6155t dt. I put that one in my calculator. Alright, so when you put that one in your calculator, let it do the integral for you, 637.2 liters. So I put at the bottom of the page here how to use your calculator to do that. You're going to hit math, go down to number 9, which is finite integral, or f and int, and you're going to press enter, and you'll be able to kind of follow from there. Put in your limits of integration. I use x for everything when I do these. Press enter. Get some practice on that. That'll really make your tests, your final, and a few other things a lot easier for all the definite integrals. That only works with integrals that have limits of integration. Okay? That is all. Like always, email me if you have any questions about the homework. These notes are posted on the website as well.